Okay, so last Friday we conclude the sections up until the divergence test. Okay. So this test is particular on it is among one of the easiest methods to check whether the series is diverged. So if you have the series and you can check the limit of its sequence, if the limit is not equal to 0 or doesn't exist, you can tell directly the series will be diverged. Okay. If the series is the limit of the sequence is 0, then it's not automatically or it's not directly be converged, but we need to check with other methods. We need to check with other method. Okay. One of the method that I want to show today is called the integral test. Okay, let's start with the series. If we have this the series of 1 over n squared. Okay. If you remember what we did last semester in calculus 1, we have the improper integral 1 over x and 1 over x squared, right? If you have 1 over x, it's going to be diverged. If you have 1 over x squared, it's going to be converged, right? So this is also similar phenomenon or similar condition. When you have 1 over n squared as your series, if you are expanding this series starting from n equal 1, and if we are going to draw the illustrations, maybe this will be the next one. Let me draw the illustration for a while. If you're going to draw 1 over x squared or 1 over n squared, okay, if we imagine this to be starting from n equal 1, 2, 3, and then 4 over there, we are looking at the area under the curve as 1 over 1 squared. Okay, this will be y equal 1 over x squared, and the area, the next area will be 1 over 2 squared. This is 1 over 3 squared, and if you have this, maybe this is 1 over 4 squared. Okay, and if we are going to increase our n, so as n going to be infinity, if we are going to calculate the partial sum, okay, if you are going to evaluate the partial sum from, let's say, I equal 1 to some n, 1 over I squared. If we check our n, this will result in or getting closer to 1.6447. Or maybe let me just write 64, okay? We can also rewrite this series if we are going to write in terms of the integral and from what we have observed, there are slight difference from this empty space, right? Okay. From this empty space. Okay. So if you imagine the whole integration, okay, so the picture all partial sums, okay, are less than this equal to. Or we can write that the series itself this will be less than 2. Okay. It's less than 2 because it has this empty space. Okay. So that's the conclusion for what we have done here. So basically, what we are looking here is if we can set up some integrations, okay, or if we have a functions or a series that satisfy, okay, for the conditions to be integrated, so we can use the integral test to check whether the series is converged or not. So that's basically what we are going to approach. Okay. Now from here, this is a little bit later. Let me write some main point of the integral test. So the first thing is we need to define the functions. Suppose the function f is continuous. It's a positive function and decreasing on, so we need to define the interval of the integrations and let the sequence become the functions of the integer. Then the series is converged if and only if improper integral is converged. So in other words, if this is convergent, then series also converge. And if divergent, then the series diverge. But okay, you need to remember the integral test just to check whether it's converged or diverged. The previous illustration is showing you it's converged. So it's not saying how converged it is, like the number or value. Even though we know that for sure it should be less than 2, but the converge itself, the convergent value itself, we cannot really determine. So that's the integral. We are just using the integral is to check the improper integral, whether it's converged or diverged. So whenever you have a function or in a series, then you know that it's continuous positive and always decreasing. Then you will know that if you integrate those functions and if it is converged, then the series will be converged. But another note for the interval, it's not always 1 to infinity. Maybe it can be 3, it can be 4 for some cases, and we need to check those intervals. This is the general interval, the general. And also a little bit, maybe I will just erase this first. This is later. And because we have learned the P test, or now we call it the P series. We need to have greater than 1 to be converged, and it will be divergent if P is less equal 1. Okay. So from just looking at the function, and you know that it's one of this kind, you can check the P. Okay, so that's the pretty much the integral test. Okay. Now the applications for integral test, okay, aside from determine the series to be converged or not, we can also use the test for evaluating or estimate the sum. Now this is okay. Now, if we look on the gap, okay, the gap on the area under the curve, okay, we need to define, we call Rn, or we call it is the remainder. or we call also this R as an error. Okay. Okay. Before, we know that we can take the limit of our partial sum. If this is to be close to be S, okay, this is our approximations, right? This is approximation. But to check whether the approximation is good enough, okay, we can use the remainder and write down that the remainder is the difference between the S and Sn. Okay. Because for sure there will be this gap, right? This is clearly like really huge gap, right? But for example, if we cut the rectangle maybe really small, maybe the error will be smaller, right? So that's how we can observe the error. Now the error itself is the difference, what we are having, the sum or the sequence or the series of the Sn, and then the number that we are already approximating. So maybe X. Okay. So the error is the difference between those two. Okay. So if you say the error is 0.1%, so that means it has the total area under the curve that has a gap around that number. Okay. Now we can take this and write as in terms of the an plus 1, an plus 2, an plus 3, and so on. So if we assume, okay, the functions is decreasing, like we in the integral test is decreasing on n to infinity, we are going to see that the error itself this will be less equal of the total area, right, under the curve. And then if we are going to have another kind of graph, now we have the overestimate, okay, and it's also similar, but what we have here this will be greater equal of the n plus 1 f of x dx. Okay. Now from these two remainder, we can take a conclusion. So conclusion, suppose f k is a k, where f is continuous, positive, decreasing for x greater equal n, and the series of a n is convergent. If Rn s minus Sn, Then we can set up integrations. This is less than Rn, and Rn is less than integral fx dx. So from this integration here, this two integration, we know at least the maximum error or the minimum error. If we have the series, for example, series of 1 over n cubed, okay. Now if we want to have the first 10 terms, or the sum, maybe the sum of the first 10 terms, we need to estimate the error. Now firstly, we can take the functions as 1 over x cubed, and we imagine that we integrate the functions because we know it's going to be decreased, right? Positive function, and it's a continuous function. We can set up the improper integral. If you maybe want to review, you can review last semester improper integral. Maybe n, maybe we start from n like that. So that we will have 1 over 2t squared limit, and then plus 1 over 2n squared. Now this results in 1 over 2n squared. This is the integral. Now if we need to approximate, if we want to calculate the series itself, if we are going to use directly approach the partial sum for n equal 10, we can take this manually or using some calculators. And this will result in 1.1975. Okay. Now if you check the remainder itself, it should be less than 10 to infinite number of 1 over x cubed dx. And because we know that this integration is resulting in 1 over 2x squared, so we are just changing 10. So this will be 1 over or 1 over 200, or the estimated error will be 0.005. So this will be the size of error. So this is so in this 1.1975, the sum, we will have estimated error of 0.005. Okay, another way for the questions is we have the error, and we need to find how many terms we will get those error. Okay. So for example, this is still the same questions, but we need to have the accuracy or the error is within 0.0005. So the Rn is less equal 0.005. And we know that the Rn, we already have this 1/2n squared from the integrations. Okay, integrations of 1/x cubed. And thus, we want that this 1/2n squared need to be less than or within the 0.0005. So we need to have or in our case, this will be square root of 1000, or is equal 31 point something, 0.6. So at least we will have 32 terms to get 0.0005. So this is another type of problem, okay, from the estimated sum using the remainder. Okay, now perhaps the previous one, it's not really this one. We just say that okay, this is the sum 1.1975. That is the partial sum of the first standard. But actually, we can also write down the remainder or estimated sum for the inequality. We can write this number into a specific inequality itself. Okay. So if we write down the inequality, if our Rn is the difference between s minus Sn, okay, and our Rn is in between of these integrations, another way to write down this inequality, if we plus Sn to all the sides or all the inequality here, we will have Sn plus this will be S, right? And this will be, or maybe Sn plus now this sounds more complete, okay? So we can state the Sn with the error. Okay. Now, if we have the same, let's say, the same series 1 over n cubed, okay, and we already calculate n equal 10, right? We already calculate the S10. Then we can write the S10 plus this is 11. Okay, and we know that the improper integral is equal with 1 over 2n squared. So we can write this inequality in terms of, so S10, we already get S10 is around 1.1975, right? So this will be plus and less than n, and then less than 1.1975 plus 1 over 2 10 squared. So this is more complete. Okay, we have the error and we have the partial sum for the first 10 terms, and we can compute, and we are having the S is in between two numbers. If we approximate this S by midpoint of interval, then the error is at most half the length of interval. For example, if we evaluate this using the midpoint method, this will be, it's still around the error of 0.0005. Which means that this number is in between what we have predicted. So that's the integral test and the estimate of sum, and then remainder theorem. Okay. So basically, the remainder will help you to find the error, okay, or to approximate some partial sums. Okay. Maybe any questions first? Any questions first? Okay. And I believe the method itself will be, or maybe the problem you will have is usually it's pretty logical, so you can actually have some predictions, just reading the question, and maybe after some calculation you will be having some prediction from your calculation that the number should be around this number, okay? And I think for as long as your conclusion or maybe your number is pretty logical around the inequality, I think that's pretty much fine for me. It's okay. Okay. Now that's the 11.3, the integral test and the estimate of sum. Now let's move on to 11.4. This is called the comparison test. So we have the divergence test, the integral test, and now we have comparison test. Okay. Divergence test is one of the most easiest. This comparison test is also among the easy to be applied. So it will be helpful. Okay. And I will admit that the integral test is a little bit tricky. It will be depend on what kind of functions you have. Is it decreasing or not? Okay, that's pretty much a little bit tricky for an integral test. But for comparison test, we can have more range to apply in the series. Okay. If you consider, we have two series. Okay. We have observed the right one. I think from the beginning we learned the series. We observed that this is the Zeno paradox. Also, we can look on. This is also the geometric, right? The sum of the geometric series. 1/2 plus 1/4 plus 1/8 and plus a 1/2 with power of n, right? And we know that the conclusion is this will be converged, right? This will be converged. Then we modify this and we take +1 at the denominator. So we know that this is converged, right? And we know that the inequality between those two are this, right? 1/2 with power of n plus 1 is less than 1/2 with power of n. It means that it's smaller. So if you have the series, it should be smaller. So if this is converged, then this will be converged. Okay? So this will be also converged. This is what we call direct comparison test. So suppose we have two series. Both series having positive terms. So if series of Bn is convergent and An less equal Bn, then the series of An converge. And if Bn is divergent and A of n is greater equal Bn, then the An will be diverged. So you need to be careful on looking the still conditions. So if Bn is convergent, Bn is here, and the series that we are going to determine is less than the Bn, then we can say that this one is, or n is convergent. And if the Bn is diverged, okay, this Bn should be going to be smaller than n. So of course, the series should be divergent. If it's not satisfied this condition, then we are unable to conclude whether it is converged or divergent. Now, how do we apply this direct comparison test? Actually, it's quite simple. Okay. For example, if you have the series, and we want to know whether this is converged or diverged. It's complicated, right? But what we can do, okay, to approach this is by looking at the fractions, and this n squared is, by polynomial degrees, it's the highest, right? It's the highest degree. So probably we can imagine this whole rational function compared with just 5 over 2n squared. Okay? And I think that's a good way to be compared with. So consider okay, and we know that this is pretty much 5 over 2 and this is a converged, right? Using the P series, this will be converged, right? This will be converged, right? And if we compare with the series that we are looking for, this is pretty much less than 5 over 2n squared, right? And we can see that from this additional, right? So 5, or maybe the series 5 is convergent by direct comparison test. But of course, if you have like maybe you need some process to prove this, maybe you can take some time to check. Okay? But I think for this one, it's pretty much simple. But if in any case you have more complicated inequality, you maybe need to solve the inequality to prove that the statement is true. Okay? Okay, another example on this direct comparison test is okay. Can we check this convergent or divergent? We can use the integral test if you want, because it's decreasing functions, right? You can check the using the integral test, or if we are going to check using the direct comparison test, we can do that as well, because we can consider the series of 1 over n. Or we call this the harmonic series, which is diverge. Okay, if we consider this series, then we need to make a statement that proves our inequality. If we check from some n, maybe n equal 1, this will be 0, and this will be 1. It seems that it's less. If we check 2, we can check out 2, it is 0.6 something, and divide by 2, this is half. The 6 is 0.3, it seems it's less. If you check 3, it's greater than 1. It's greater than 1 over 3. It seems it's great. So it has less, but then after n equals 3, it will be 3. So we can make conclusions. Okay? If this happens, we can make conclusion that this is greater than 1 over n, but the n should be start from 3. Okay? And since diverge, then this is also diverge. Okay, by direct comparison test. Okay, that's the example. Now I think we can have a short break, and we can continue after the break. Okay, let's continue. So the comparison test. Okay, so this one we still can check the using direct comparison test. So this should be satisfied through some condition for the series to be converged or diverged. Okay? But this direct comparison test has some weakness. So if we consider another example, let's say we have the sum or the series of 1 over 2 with power of n, but minus 1. So it's not plus 1, but it's minus 1. If we want to compare this series or this typical function here, okay, let's consider the 1 over 2 with power of n, our geometric series. We know that this is converged, right? But from this inequality, what we get is we are getting the it's greater. And from the direct comparison test, we cannot really conclude if this is converged or diverged. Now what we can approach is we are going to use another comparison test, okay? And we are using the limit. So let me write here, we cannot conclude whether the series is converged or not. Now the method is called the limit comparison test. Now suppose we have two series, AN and BN, both with positive terms. So if the limit as n approach infinity, of an over bn, it's equal c, and c is a finite number, and c is positive or greater 0, the conclusions will be the series both either converge or diverge. Okay. Now, the idea behind this limit convergence test is to find this limit. Okay. Find this limit. So to find whether it has a constant c, which is a positive c, and it should be greater than 0. So if you have this 0, it's also, you can conclude whether it's converged or divergent. But then if you have this c, you have to prove that this is a finite number and positive c. The conclusion will be if both converge or both diverge, which means you need to know the other series condition. So if Bn, we know Bn is for sure it should be diverged, then if we get C, then An also diverge. If Bn is converged, then An is converged as well. Now if we are going to look on how to make this these tests are proven to be true, then we can take some time to check the inequality. Okay, let m less than c less than the capital M. Okay. And m, both m are positive positive numbers. So both are positive numbers. And let An over Bn is close to C. That's our definitions with limit actually. And then we have this this inequality. This is when n is greater than capital N. Okay. And also we can write down in terms of, if we cross multiply, so from here we know that because An is in between this Bn, then if one of those diverge, then also the An, and one of those converge, also the An. I hope you get the idea behind this. Okay. So this 2m is a positive term, and we define our C as An over Bn, for to be we use limit and it will be close to this number C. And then from here we can imagine that we can set up our inequality and make it into Bn, Mbn plus An plus Mb. So then whenever the other part is converged or diverged, okay, for example, if Bn is converged, of course An will be converged. If Bn is diverged, An will be diverged because we have this Bn cover both sides. Okay. Now, if we are looking back the series 1 over 2n minus 1. Okay. Now, by looking at the limit conversion test, we can set up this series to be having An and Bn. So let's say our An is our series that we are looking for. our Bn is just 1 over 2 to the power of n, because we know this will be converged. Then we can take the limit and then we can solve this limit. Forget the limit. Okay, don't forget the limit. Then this will be equal 1. And this is basically greater than 0. It's a positive terms. Then we can conclude that limit exists. And since the series of 1 over 2 with power of n is convergent, then the series also converges by limit comparison test. So whenever you find usually a rational functions, it has a fractions, maybe the first thing you can check the divergence test. The second one, you can check the direct comparison test. I think that's the most logical one. If it seems that you cannot have a conclusion from direct comparison test, you can directly go to limit comparison test. Okay? But anyway, if you just go directly to limit comparison test, you should be able to find out easily. No need to go to direct comparison test. Because if you check the limit and you get the positive number, then you can conclude what your result will be. Now, if we looking at another example, okay, we're looking at another example. Okay. If we have this, it seems complicated, but if you look this function and remember how to deal with the highest degree of polynomials, and we can imagine how to compare this with other series. Okay, it's either that you go to direct comparison test, or we can just directly go to limit comparison test, which is more feasible, and I think it's the calculation is just calculating the limit. You find the limit. So, for example, we can take the an to be our 2n squared plus 3n and then we can compare with the other Pn, which is we just take the highest degree of polynomials, so 2n squared for the numerator, and the denominator will be square root of n with the power of 5. Or we can take this and maybe we can more clear seeing that this is actually okay. And this Pn, you can imagine the P series also is less than 1, so it should be higher. But then if you going here, an and bn, we can just directly using the limit conversion test. So we can take the limit and then take the ratio between an and bn. We take those ratio. So go by limit. So we can multiply this is 5/2 plus 3n, 1 plus 1/2 is 3/2. This will be 2, 5 plus n to the power of 5. The highest degree will be the 5/2, so less than the 5 with all with n to the power of 5/2. This is also the same, 5/2. So we will have three over n, and then 2. This is 5 and 5 plus 1. Or this will be equal with 2. And this will be 2 square root of 1, or we can have 1. So this 1 is positive. And we can write down, since it's diverge, because it's P series, P is less than 1, then the given series, or the series of this function, also diverge by limit comparison test. Okay, there is also estimating sum in this one, but I don't think it's really helpful, because basically the estimating sum is the same with the integral test. So I will just skip that. Okay, so that's the comparison test. So we have direct comparison test and limit comparison test. Okay, but the more practical one is just using the limit comparison. And my suggestion is just stick to the limit comparison. But somehow, if you see that some series will have, or you can prove using the direct comparison, and then you can just use direct comparison. But for somehow, they're slightly a little bit complicated, and you are not sure whether you can prove whether an is greater than bn or bn is greater than an, then just using the comparison. So as long as you get this positive number here, and this should be okay. Should be fun. Okay, now the next method, that will be the alternating series. So this is 11.5, the alternating series. Okay, let me just give you a brief recap. So far we have done sequence. Okay. Sequence is very introduction, and using the limit to get into the sequence. Okay. And then you can have the series, the geometric series, right? And then you have the test of divergences or divergence test. That's to check directly whether the series is divergent or not. Of course, you have the P series, and the P series using the similar approach like the improper integral. You can have the 1 over x and 1 over x squared. That's the most easy graph that you can imagine visually. So divergence test, and then integral test. If you have the functions, the continuous positive functions always decreasing, then you can use that integral test to check convergence or divergence. Integral test. And then you have the convergence test. Convergence test has direct convergence test, limit convergence test. Okay. So as long as you can consider some known series that are converge or diverge, you can check the inequality. And my suggestion is just go directly to limit convergence test. If it has positive in the limit ratio, then you can go conclude the series. And now we have the alternating series. So alternating series means that the series will have alternating signs. So positive, negative, or negative, positive, negative. Now, if we look at the example, so we have 1 minus half plus 1 over 3 minus 1 over 4 plus 1 over 5 minus over 6, and then maybe we can write this in terms of this is the pattern. Okay. Or we have from negative half plus 2 over 3 minus 3 over 4. This is just an example. So using the negative 1 with power of n, or negative 1 n minus 1, or n plus 1, we have also another terms. If you have this kind of one, negative 1 with power of n, then it should have this described that the series should have the alternate signs. Okay? And there are several conclusions. Okay? If you imagine the alternate series. Let me write down what the theorem of this alternating series. Okay. So we start by the alternating series test. Okay. If we have if this satisfies first is we have this the number or the terms after the first one is less than the previous terms, okay, for all n, and then the limit of the Pn of the sequence itself is 0. We can set or conclude that this series is convergent. Okay, now this is just a theorem, right? How do we make sure ourselves that this theorem is probably true? We can draw the graph. Okay, we set up to be imagining that the limit of the sequence is getting 0, and then the terms is getting smaller, smaller, and smaller. Okay. So first we can draw. Let me check if I have the drawing. I have. Okay. Let's set up just a number line, and this is just to show you the series, or we have the partial sum here, and this is the series how it looks like. So we set up the first term b1. Okay, it's going on here. So this is the partial sum 1, right, s1, and then the value of this the next term should be less. Okay, the b2, but it's alternate signs. It's minus. Okay, it's minus. Maybe just like it's smaller than b1, right? So this is our s2, or partial sum from the two terms. Okay? And then we plus again. It's also smaller than before, and we are going to have, and probably we will have some terms and end up with this one right here. What we are saying is that the limit is actually getting smaller and smaller and smaller, and eventually this is what the conditions are. Okay? When you have the terms is less and the limit is getting closer to 0, then of course you should have the convergence series for the alternate sign. I hope that the graph is helping. Okay? So you can imagine like it's getting smaller. Okay? You plus from the beginning like a big number, and eventually getting smaller in terms of value, but it's always alternating. The signs always alternate. So plus minus plus minus plus minus plus minus, and eventually it's getting the limit is getting 0. Okay? Okay, we can also have some proof for this alternating series, but I think I don't really need to take this proof for you. But let me just give you another visual or example, okay, to look on. Okay, so if I give you the example alternating harmonic series, start from 1, negative, and then plus, and then negative. Or if we have the pattern or the formula, this is the formula. And if you check the conditions, okay, it's always getting smaller, right? So we know that the bn plus 1 is always less than bn. And we can also prove this through our algebraic expression in equality. We can have this, and then 1 plus 1 is less than 1 over n. Okay, of course this is going to be true, right? And so this is first. And second, we can have the limit of bn, which is 1 over n. This is 0. Okay? So this is these two statements are true. So which means that this series will be convergent by alternating series. So we can say that the harmonic series in alternating signs will be having a converge or convergent series. Okay. Or if I have the graph, let me draw the graph. if we pinpoint all the n from n equal 1, if we compare with the an, it's going to be having 0, and the limit is going to be 0. And the partial sum is getting to have some value here. We check from 1, and then n equal 2, 3, 4, and sometimes some enter. This is how the visuals looks like. Okay. Okay, in alternating series, we also have the estimation, the estimate sum. So if we have S is equal sum of 1, n minus 1, and then Bn, where Bn is greater than 0, and the sum of alternating series that satisfy then we will have the remainder which means that this is the same problem as the integral test, okay, the remainder. So we will have the error, this is the error or maybe the accuracy. So we can check the error by looking at how many terms we have. Like maybe we have some n equal 10 probably. So this will be S10 and this will be 11, right? N plus 1, 11. So we can just look by B11 and that would be our estimate value for the remainder. Okay, now I think this will be the last section on the alternate series. It's called the absolute and conditional convergence. Probably next Friday I will review and giving you more examples. Okay? So in alternating series, we have conditions that we can state. It's absolute convergence and conditional convergence. Okay, let me start with the definitions. Okay, the series of AN is called absolutely convergent if the series of absolute values is convergent. Which means that we are looking on the absolute value. So if we have alternating signs or alternating series, we can check the absolute value of those series and check whether the absolute one is converge or diverge. Okay. Because like the previous case, the harmonic series, we have the alternating harmonic series, which is converged, but the harmonic series itself, without the alternate signs, it is diverged, right? So this means that there are conditions that the series is supposed to be diverged, but when it has the alternate signs, it becomes converged. So that means the convergence is conditional. Okay? But here, what we call it absolute is when we have the series itself is already converged without the alternate signs. Okay? So we can say that when it has the alternate sign, for obvious, it will be converged. We say that conditions is absolutely convergent. Okay? That's absolutely convergent. So if we probably having an example, let's start from this n squared, 1 over n squared. Okay. If we look on the absolute value, then we will have just 1 over n squared. And since we know that this is a P series, okay, the P series, P is equal to, which is P equal 1, then the series is converged, right? Then we can conclude from the definitions, then the series, this one is absolute or absolutely convergent. Okay. So that's the first definitions for the absolutely convergent. The second, like I mentioned before, is a conditional. Okay. So the series is called conditionally convergent if it is convergent but not absolutely convergent, or that is if the series converge but the series of the absolute value diverge. I think the last part is pretty much conclude the terms. Okay. And we call this conditionally convergent. I think we can take the example from the harmonic series that I mentioned before. Maybe I'm just writing the series. That this is convergent by the alternating series theorem. It's getting smaller terms, and the limit is 0. Right? The limit of this sequence of 1 over n is 0. So this is converge. Okay, this is converge. But okay, if we check the absolute value, and using the P series, that this is diverge using the P series, P equal 1. Okay. And then our conclusions will be this series of the alternating series is conditionally convergent. So we can determine the series either absolutely convergent, conditionally convergent, or divergent. So we are not looking just converge or diverge, but sometimes, in some cases like this alternating series, we may have conditionally convergent or absolutely convergent. And usually, in some cases or problems, the question is asking you to observe whether it's absolute or conditional. So that means you need to use this absolute value to check whether the series is converged or divergent. Of course, we are just looking on the practical example like 1 over n or 1 over n squared, which is easy to be determined. But sometimes when you try to absolute, taking the absolute value, maybe it has some terms, and maybe you need to use another method, like limit convergence test, or maybe just divergence test to check. So, in some problems, maybe you need to have some logical steps, like which method you are going to use for. Like alternate series, the first thing you can do is you can check the absolute value and looking the series itself first, and then you can try to develop the methods first. Okay, maybe you need to check using the integral test probability, convergence test, and when you have those already determined, either converge or diverge, then you check the alternate series, and whenever the series having like this, the next term is smaller than the previous terms, and the limit of the sequence equals 0, it should be converged for alternate series. And then you can take the conclusion whether it's conditional convergent or absolute convergent. Or even when you have this and this series is maybe, if this is diverged, then you can just directly say it's divergent. So when you have the alternate series and it seems that it's going to be diverged, then probably it will be diverged. And let me check the time. Okay. Okay, probably next Friday I will go through some example and review and going to the next one, which is the ratio and root test. Okay. So chapter 11 is probably the most, one of the most, it's a simple structure, but there are several sections. Like we have, this is 11.5. So we will have at least until 11.10 or 11. So it's like, because there are several tests, several methods to check. So there will be, and there are, in some cases, we are going to look on what we can represent from the series or sequence with the functions, and we can also have some applications in later parts. That is, I believe will be related to your advanced courses later on. You will not see now, but maybe later you will see the connection. So I will just stop until here, and maybe later I will also give you some attachments for some practice and exercise for chapter 11. And yeah, I think we will continue next Friday.